Okay, the next thing we want to look at is here, exercise 2.5, the NBA data. Suppose you would like to know whether older NBA basketball players attempt free throws more or less often. In the file NBA combined.xlsx, select the data corresponding to a team of your choice. Got the data here, and there's quite a lot. It goes on for a while. Got a couple of different teams in here, and see if we have all of them or not. And we can see if we're missing any individual players. This is about 10 years old, this data. But what I've got is the name, player, I've got the age of a player, I've got the team that they're playing for, which Utah Jazz here, and I've got their free throw rate. So this is free throw attempts per field goal attempt. And basically, I just want to model this as a function of the age. And there may be some sort of a story about the younger players playing particularly well, but then getting more experience and dialing it in to some extent until they start to decrease in their playing skills again. So, okay. What this exercise asks us to do is just regress the free throw rate on age and interpret the coefficient age. So, I'll do that. I'll take the Utah Jazz here and go ahead and say data analysis, grab the regression tool, and let's let FTR be my dependent variable. I'll go all the way down. For X, take age. I did take labels. Suppose I need the residual, but I wouldn't mind seeing something like a line data look. And yeah, okay. So there's my line fit plot. Interesting. So no zero or negative ages here, but as you see, it's pretty noisy data. And what do I have for age? Here, my coefficient for age says not statistically significant. But if I did interpret this as statistically significant, I would say that for every 1 year increase in age, my predicted FTR for a player is going to increase by point. But again, standard error here is 0.03, p-stat is 0.39455. That looks like a genuine noise result. That looks like just happening. And r squared, again, basically 0. Tiny, tiny sample, so the degrees of freedom in adjusted r squared is giving me a negative adjusted r squared. Very amusing. Not really supposed to happen, but it can happen if the model had enough. So that is one example. Notice that I've only taken one team, and I can go back and I can do it again for the next team and the next team, which is where part number 2 comes in. The histogram below shows the distribution of the age coefficient estimated separately for many NBA teams, not all included in the data file. Well, if you're still hesitating in interpreting what the t statistic and the p-value are telling you, this is it. The idea is basically you could collect a sample many, many times. And in this case, I do in fact have many separate samples of separate NBA teams. So here's the Jazz, and then, okay, more and more and more, and quite a few teams in here. Each of these teams is going to give me a separate regression with a separate coefficient on age. It may very well be that there is a true population. Get all of the data from all of the basket players that ever existed or ever could exist. There might be a true relationship between age and the free throw rate. But each of these teams in isolation is just going to give you one number, and it'll be a different number every time. So estimated separately for many teams, not all included in the data file. Use your estimate and this histogram to explain the difference between a population parameter and a sample estimate in this context. I have a sample, just the Utah Jazz here. And what did I get? I got 0.01259. That's my sample statistic. That's my sample slope of a regression. When I go to the histogram down here, I see that, in fact, there's variation across all of these teams. Now, this is what we call the sampling distribution. It's the distribution of that statistic if I could collect the data many different times. or if I looked at many different teams and estimated coefficients. The difference between the sample statistic and the population statistic is that there is a true number. If I could get all of the data in the universe from all of the teams going all the way back across the years, there is a true number. And every time I collect a sample using a small amount of data, I'll get a different number that is hopefully close to the true number. The true number is somewhere in here. I don't know where it is because I don't have all the data in the universe. But I do know that, for instance, what I found for one team, 0.01259, is going to be somewhere around here. And then other teams are going to give me other numbers, which actually look like they're usually less than the number that I just found for the first team data set. Right, so many different samples, many different sample coefficients here, but there is one true population number I would have if I was able to collect. And then we can say something about the size of the sample and how close these numbers would be to true population, which is sort of what's coming here. Remember, there are three magical things that will affect the sample standard error of the coefficient that a student estimates the above model for Memphis. He says the following: I found that beta 0 is equal to 1.149, your intercept, and beta 1 is equal to negative 0.027, so I know that FTR is equal to 1.149 minus 0.027 age plus an error term. What is wrong with the student's statement? Well, notice that the student here did not give us any sort of a measure of confidence. There's nothing probabilistic about this statement. These are not the real numbers. These are the real numbers for his sample, for Memphis, for the line, but these are not the real numbers for the population. If he's just talking about his sample for Memphis, then perhaps we can roll with these numbers and treat them as something that we take very seriously. But if I try to take these numbers and extrapolate to anywhere else, I'm going to be in trouble. So it would be better if we could say perhaps a 95% confidence interval for this number and a 95% confidence interval for this number. That would be very helpful. Or anything at all about if you give me an age and I predict FTR, I can give you a confidence interval for that. Some sort of a probabilistic statement would be preferred here instead of taking the slope and the intercept from one sample and rolling with them as if they are absolute. Also, I don't know if this coefficient is any different from 0. And so if I have a lingering question, statistically speaking, any different. If I have a lingering question about whether this number is just noise in my sample, it's not really expressed here how confident. So there are many things that we can do to improve communicating this information and giving some sense of whether it's precisely estimated or imprecise. Point 6. Um, by the way, I would comment that if you just fit a scatter plot in Excel and right-click on the data and say add a trend line, and then say add the equation of the trend line, what it does. Everything that we've done so far in this class is in terms of discerning whether or not you can make a reliable decision based on these numbers, which is not a function just of this number, but also of its standard error. Something to tell you about whether this number is really different from. Okay. Suppose the graph below shows the sampling distribution of the parameter from exercise 2.5, same data, estimated across a set of similar teams. Draw the sampling distribution you would expect to see if you instead estimated that parameter with samples of teams which had each of the following characteristics. So we're going to change things a little bit. I notice here that when I have many different teams and I estimate this, get a shape like this, right? So there's some variation in. But what if I had, say, more players? Okay. I'm going to pop over to the whiteboard, and I'll start with red, apparently. Do that again. I'll start with regular distribution. This could be any kind of distribution. It's a little bit skew, so maybe it looks like the data that we just saw. I don't know what this shape is going to be like exactly, but let's suppose that this is the distribution that we got. The version of this that we just did, where I take, well, not that many observations per team, right? But many teams, and I estimate the coefficient several times. I'd have numbers like shape is this set of axes. Then we're just getting a general question about what would happen if I change parameters. Well, you know that there are three magical things, right? The three magical things that would affect the shape of this. We'll start with more players. Okay. Standard error of beta 1 hat is something like sigma of epsilon over square root of n times sigma of x. Standard error, not the variance. If you're thinking variance, beta 1 hat, sigma squared of over n sigma squared of x, something like that. But we've got the three magical things here: population size, the amount of variation in error terms, or variable on the right-hand side of the model. So in this first example, if I had more observations, a greater sample size, that's in the denominator. I should have a smaller standard error. And instead of this picture, which I've currently got, I should have a skinnier picture, right? If the truth is here, and I expect to see numbers close to that value, and I'll say that this is perhaps the true beta 1, call it beta 1 now, then I should get something like that, skinnier and closer. And if you're wondering why I made it taller, it's because the area under the curve is supposed to integrate, it's supposed to add up to 100%. So if I make it skinnier out here in the tails, then it needs to be taller here, center. That's the best way. How about a greater unexplained variation in the dependent variable, which is free throw percentage? Well, okay, that's the error terms. So if there's more variation in the error terms, expect a shorter and fatter distribution. It'll go way further out in the tails. I'll have more of these extreme values. So perhaps a picture like that. Next one, older players. This is interesting. This is a bit of a troll, actually. It depends on the relationship here. If I just have older players, here's my scatter plot. Suppose that there's a line. If I only have older players, and this is a well-specified problem where there really is this tubular kind of shape to the data, we might call homoscedastic, and nothing else of interest is going on here, so I just take a sample of data up here where the players are older as down here where the players are younger. On the x-axis, well, the regression line up here for the older players is the same as the regression line down here for the younger players, and I can still estimate it. If I only have the older players, meaning I have less variation in x, the variation in x is given here in the denominator. So less variation in x, in fact, means a shorter, fatter distribution again, a less precise estimate. Be a bit sad. But if I just have older players and there's the same amount of variation in those players as there would have been for a different sample that had younger players, then perhaps there's no. This is interesting when we talk about sample selection bias. So a scenario where your sample is not entirely representative of the population you intend to study. If I only pick, in this case, the older players. Well, imagine the NLSY data where I was looking at the relationship between earnings and years of education. If I only picked people who had a lot of years of education, say a bachelor's degree or higher, this is not the entire population. Can I still do this study? Because the selection is based on the variable x instead of the variable y or something that has a weird relationship between the two of them, this is actually okay. as long as I have a sample of x that has the same relationship as every other sample of x between x and y, then sampling based on x is actually fine. But generally speaking, we're a little bit, how should I say, it's a little bit disturbing when you see something like that. And one of the things that could happen is perhaps I have a slightly misspecified model. So suppose my data look like this, and I've deliberately drawn some curvature to it. So maybe the best model is something like this, which is not a line. Okay, well, I didn't know that, and I just estimate a line. Now what will happen? If I have this sample of older players, the line is a little bit flatter. And if I have this sample of younger players, the line is a little bit steeper. So I'll get a very different beta 1 rise over run, depending on whether I have the older players or the younger players. You need to know a little bit more about this story before we can discern exactly what's going to happen over here. But if for instance, this was introducing bias and making the slope of this relationship smaller, then maybe I have something right, my distribution to the left instead of being where it had been originally. Yes, the center of this distribution is now well under where the original beta 1. Okay, take that away because it could go many different directions. This one is very open-ended. But the last one here, a greater spread in the age of the players. All right. So 1, 2, and 4 are the 3 magical things that affect the standard error. So 1, 2, and 4 are this story, and then 3 is this kind of imagine some more complicated scenarios. Number 4 says greater spread in the age of the players. Okay, so that means a larger sigma squared of x, which means a larger sigma of x, variation in x, and that again means more precise estimate. So in the limit, as I have lots and lots of data or lots of variation in the x variable, I should get very, very precise estimates where all of my estimates very close to the truth here and nothing out here in the tail. This is good. Beautiful picture. Okay. The next piece here, moving away from the NBA, is a bit longer. So let's see about this. 2.7, simple regression. This practice assignment will test your ability to perform the following objectives. My goodness, it's a long one. Determine the appropriate dependent and independent variables for a model. Okay. Use software to estimate a single variable regression model. Locate and explain the values of estimated coefficient and intercept in output for a single variable regression model. Now you should have lots of practice at that. Locate and explain the meaning of the R-squared value in output. Locate the values of the explained sum of squares, the explained part, right, the regression part, the total sum of squares and sum of squared residuals on output, or calculate them from the output. Again, by now we should have lots of experience with these, and most of that ANOVA table should be reasonably straightforward, with exception of the shape of an F distribution and how the F distribution translates p-value, sort of beyond the scope of the course. Those main points in the ANOVA. And the table at the top of a regression output from Excel and the coefficient at the bottom of a regression output from Excel should be reasonably sensible. Okay. Locate the values of all of those, locate and explain the meaning of the standard error of regression in output, which is wonderful. That's basically standard deviation of the residuals. Assess whether the values of an estimated coefficient, intercept R-squared, or standard error of regression are sensible for a given situation. Identify and explain the meaning of the standard error for a coefficient. Okay, the data file for this assignment is heat.xlsx. Go ahead and close the NBA data since we're done there. Don't save. The heat data. There it is. Good, good. Some more old data from the ancient times. And what do I have? Natural gas and the temperature outside. Goodness, this must be in Fahrenheit. Okay. The dataset provides information on monthly utility bills from Niagara Mohawk, a utility provider in upstate New York. Once again, this is one of the sample datasets that comes with the Stock and Watt textbook. It may be helpful to know that natural gas is primarily used for indoor heating, but is also used in smaller quantities for cooking and hot water. Accordingly, most households use relatively little natural gas in the summer. If anyone is working at a utility, or if you're just working in a field where you have very seasonal demand, so a lot of consumption of your product in one time of year and relatively little consumption of your product at another time of year, this is kind of a nice little snapshot example. Natural gas usage is typically measured in units called therms. And something that I do in this class a lot is go on and on about the units and why the units are important. This is another fun example because we've got temperatures in Fahrenheit. The international can be a little bit bizarre when you see a temperature like 70 degrees. Okay, well, it's nothing is on fire. It's just Fahrenheit units. And then therms for natural gas. Natural gas has therms, and there are other things like MMBTU, but therm is a unit that most people are not familiar with. The average American household used just under 2 therms per day in 2009, and the average US temperature across locations and times of year is 52 Fahrenheit. Interesting. Okay, so some good trivia there. Suppose we would like to know how temperature affects the usage of natural gas. Well, here's a business case. Do you believe that the temperature outside affects demand for your product? Do you believe that the time of year affects demand for your product? Do you believe that some other variable that perhaps you have available in machine readable format affects demand for your product? If so, you may be able to estimate the relationship between your sales and that other variable. This one's really obvious. Temperature affects the usage of natural gas. Which variable is an appropriate dependent variable? Notice the phraseology here. Temperature affects natural gas. So, natural gas is affected by temperature. Natural gas depends on temperature. The dependent variable, the outcome, should be natural gas usage. Which is an appropriate independent variable? That should be temperature. I do not believe that natural gas units usage directly affects temperature outside. Maybe in the long run, there's some sort of a global warming story, but I don't think that the temperature outside is directly influenced right now in a large or meaningful this type of data way. Temperature inside is being affected by the use of gas. Unless you're in a big city, that's not going to cause any. Although in big cities it does. All right, so explain your choices. Natural gas is depending on the temperature, so natural gas is dependent, and I will use the temperature for X. Find the mean and standard deviation of your dependent and independent variables. Explain whether these values seem sensible to you and why. Well, that's easy, regular analysis. These are things that we've done many times by now. So let's say over here equal to average of gas. That all the way to the bottom. And 7. Okay, interesting. So date. B, it's monthly data. So monthly data, natural gas, 14. Fair enough. What about the temperature? Average numbers over here. Average. Average temperature. And the average temperature is 48. Well, let me back up a second. Because we're told natural gas usage is typically measured in units called therms. The average American household used just under 2 therms per day in 2009. The average US temperature across locations and time of year is 52 degrees Fahrenheit. Okay. Therms. Information on monthly utility bills from Niagara Mohawk. Monthly numbers. 2 therms per day in 2009, and this is in New York. So I've got more than 2. I've got 7 for my average. It's New York. And is this daily? Are these already adjusted? If this is January of 89, if it's already adjusted to be per day by the number of days in the month, and this is 14 per day in January of 89, well, New York, northern part of the country. So 7 instead of 2 is perhaps plausible. And then what would I say about 48? Well, if 52 is the average temperature across locations and time of year in the United States, interesting trivia, 52 degrees Fahrenheit, but here I've got 48 in my sample. Well, again, it's New York. So, northern part of the country, if that's the average temperature, it doesn't seem particularly surprising. Yep. All right. Seems plausible. I do have a theory that that data is already in daily average. Okay, all right. Well, and why? Should we look at standard deviation? We may as well. Equal to tdev dot s. So standard deviation for the natural gas data. It looks like this stuff varies, from as low as 1 to as high as 14, the highest number I see right now. 15, there's a 15. So standard deviation of 4.687. Yeah, from 1 to 14. Okay, let's 14, 14. 1 to 15 would be a range of 14. Divide that by 4 and you'd have 3.5. Yeah, sure. 4.687, like a do the same for the temperatures. And I'm guessing that we would 10 st ev dot s of the temperature data. And what's the result? 17. A little more variation than I expected. So New York, lowest temperature I see here, I've got a 72. All right. Okay. How hot does it get? And this is probably monthly average as well, because he's like monthly data. Well, fair enough. 17 is a standard deviation, but low double digits makes sense. Estimate the single variable regression using the dependent and independent variables used. Well, let's see if natural gas usage depends on the temperature. Go to data, grab the regression tool from the data analysis tool pack, and for the Y range, I'll take natural gas, dependent variable. For the X range, I will take the temperature. I am including labels. Line fit plot? Yeah, I think I would like a line fit plot. I'm curious. And hit OK. There's my line fit plot. Bit of a mess. Doesn't look perfectly linear. Maybe has a bit of a swoosh to it, but I'm going to read much into that. Get that out of the way. Zoom in a bit. There it is. Goodness gracious. We just saw the line fit plot. R squared is almost 96%. So it makes sense with as much variation as we saw in that plot that R squared could be high as it is. On the high temperature days, we have very low natural gas usage, and on the low temperature days, we have very high natural gas usage. So that checks out a lot. In fact, you might think about it and say, what are the other variables that affect natural gas usage and make it high or low? It does make sense that the temperature would be the driving factor, perhaps the dominant factor if it's explaining 96% of the variation in the usage of natural gas. Natural gas otherwise is just being used for cooking, which essentially doesn't vary, and then maybe running things like water heater in your home, which also doesn't vary very much with the time of year, so that might just get washed away by intersect or Y bar. So the variation being explainable by the temperature outside, I absolutely believe. I'm not surprised to see a giant R squared like 96. As for the sign of the relationship, I see that indeed, when it's warmer outside, people are using less natural gas to heat their homes, which makes perfect sense. And when it's colder outside, people are using more natural gas. In terms of the units here, each additional degree of temperature, degree Fahrenheit, corresponds to this model predicting about 0.26 fewer therms of natural gas use. Right. Write a one-sentence explanation of each of the following: the y-intercept, slope, r squared, and the standard error of regression. So I'll just talk through each of them. I've got the y-intercept says when the temperature is 0 degrees outside, y-intercept is where you hit the vertical axis, right? So the temperature would be 0 degrees. This model predicts that the consumers in this area would use on average 19.17 therms per day, which is quite a lot, but also 0 degrees outside is very cold. So that's pretty reasonable. Then the slope. Well, I just interpreted the slope. For each additional degree Fahrenheit, in terms of the temperature, the model predicts that the users in this area are going to consume 0.26 therms less per day of natural gas. As for the R squared, well, R squared says that this model, which includes only the temperature, explains 95.6% of variation in usage of natural gas. And standard error of regression, a typical residual in this model is about 0.987 therms. So this model usually predicts within 1 therm, or 0.987 therms, of the correct usage, conditional on temperature. Pretty good. Reasonably precise, lots of the variation. 5. Suppose that you collected similar data from a different region, but you collected the same number of data points, and you believe that, oh no, is this one of those 3 magical things questions? You believe that households use similar amounts of natural gas for a given temperature. What do you think the slope coefficient would be if estimated the same regression? Explain using relevant values for your output. Okay, think about this. You collect similar data from a different region, somewhere else, the same number of data points. So the data size does not change. N is the same. You believe that households use similar amounts of natural gas for a given temperature. What do you think the slope coefficient would be if you did the same regression? Now, if I choose a region where X doesn't change, I might have a less precise estimate coming from here. But it's just asking what you think the slope coefficient would be. If I have to guess one number from a different region, but maybe a similar region, households use similar amounts of natural gas for a given temperature, my best guess is that my estimate is going to be close to the population parameter. And I don't know what the population parameter is, population slope, but I do have an estimate of it right here. So my best guess is that when I go and I test this in another area, I should find a slope that is sort of like negative 0.26. And I can be a little bit more precise than that because I do have confidence intervals here. So this says if, for instance, there's a 95% chance that the true population parameter is in the range, or if the true population parameter was this number, then there's a 95% chance of seeing sample estimate in this range. I can interpret this confidence interval as the set of values that I should see about 95% of the time. So if you want to tell me one number that you expect to see the most, this is probably your best guess. And if you want to give me a range of numbers that you expect to see with about a 95% chance, then this is probably your best guess. This upper and lower bound that we. Okay. That is the end of these exercises for Module 2. So I will finish it right there.